Well, good morning. I hope you all enjoyed the party last night. I know I did. I hope you didn't have too many beers because we have a full day today as well. And we're going to start off with Daniel and Daniel from Omegapoint. They're going to teach us all about what happens beyond the lambdas.
Yes.
So,
All right. Thank you so much. So this talk about beyond lambdas, the aftermath, what is it all about? Well, when Daniel and I started working with Java 8 2 years ago, we made all those rookie mistakes that we would have done as beginners. But we're both senior developers. And then after
we both dabbled with functional languages before too, so it wasn't totally new.
So the thing was that we saw the same mistake coming in over and over again because there were new developers introduced to the project. So we figured that, wait a minute, this is probably a paradigm shift in the Java language that creates this kind of problem. So for this talk, we decided to let's pick a lot of our examples and present them for everyone so they can actually help either junior developers or beginner senior developers into moving into a more functional type of language like Java 8 is nowadays. So let's take it away. Oh yeah, this is a boring slide. Please Google us if you want to find out something about us.
Yes.
So let's do some coding because we don't want to do slides. First example coming up. Okay. Hope you guys can see this. Yes, we can. Great. So the first example is a very trivial one. And it's a map or else of an optional. And the common mistake in this part is that developers tend to think of the or else case as the else branch in an if statement. That means that if the map doesn't exist or the map doesn't get executed, we're going to execute the else branch. But a matter of fact, the optional is just a data structure with an API on it. So in this piece of code that we see here, we are actually going to execute both branches or both methods, the map and or else, because or else is eager. So in this case, the advice won't be cheap. It will be both cheap and expensive. So Daniel, how would you have fixed this one if you did it the right way?
Well, I think we should discover the other type of or else, the or else get that we have on an optional that takes in a supplier as an argument. And the supplier, we can write that as a lambda expression or a method reference. Now we get kind of a lazy execution of this method instead.
Right.
So we fixed the problem here.
But another thing that you just saw there was that IntelliJ suggested or else as your first choice. And I think that's one of the reasons why people tend to pick that one the first, because they're so focused on handling the optional, that new thing. And this talk now will actually focus on optionals. We're going to look at functions, streams, and lambdas. So let's move on.
So we started to warm up. Okay, so let's look at this example. Here we have a method that takes an optional as an input argument. It's called underscore, but it could be called anything, like process orders or whatever. So what we're doing here is pretty straightforward. We have an optional, we map it by calculating some other value, and then we apply a filter on it. We're applying some criteria on it. And then if the criteria is fulfilled, then we map it again by transforming it. And if we didn't have a value or if we didn't pass the criteria, then we apply a completely different calculation. Pretty straightforward code, right, Daniel?
Yeah, I mean, looks
like Java 8 style.
Java 8 style is a lot of flat. Oh, that's not a flat map. It's a map, filter, map, or else get. You seem like a good developer when you actually made to do all of this stuff, right?
In one line.
In one line, yeah,
Pretty
exactly.
Cool. So can we improve this in a way?
Well, I think the best way to show what really happens is to move over to the pre-Java 8 style, and it would look something like this.
Okay, so we've just rewritten the entire logic by using like standard Java style. So if we look at this, I think it becomes pretty obvious that this method is actually doing two things, right? We have the first if statement, which do we have the value, then let's do a couple of things. And if we do not have value, or if we didn't pass the criteria, then do something completely different. So what we're doing here, in this case, we're violating the single responsibility principle. But it's very easy to miss that because we were writing this beautiful optional map, flat map stuff. So we forgot, suddenly we just forgot the good design practices that we all know.
Oh man, that SRP is hunting me back again.
So how can we solve this problem? Well, we should only do one thing in each method. So instead of passing in an optional, we should just pass in a real value. So if we rewrite this, and the first calculation method here is what the first if statement actually did, and it's taking a concrete value. So we can take the input argument, and we can flap map the result of the first calculation, and then we apply the or else get, which does the completely different calculation. So now we have a method that does one thing, and the actual forking is handled before the method.
But Daniel, I mean, isn't this... I understand the forking part,
Yes.
and we should do that right away. But optional, wasn't that a means to protect you from, nulls? So if I get that value, I want to pass it on to some other method that can handle the stuff.
Okay, that's cool. Well, let's look at another example that talks about that. So we want to avoid Nullpointerexception, right? That was like the holy grail for some. So here we have an argument. It's still an optional, and we just do something on it if we have a value. So let's try to rewrite this again to non-Java 8 style. See what we're doing here, actually. So we have a method that takes an argument of type T instead of an optional of type T.
Okay. Oops.
So if there is no value, which would be, I guess, if it's null, then don't do anything. And if it's not null, then do something. So what we're seeing here is, what is this? It's defensive code. You suddenly said that I have a method that accepts bad input. Why do you want to accept bad input? Most of us wouldn't write code like that, right?
No, I agree. I guess what I really wanted to do is that I have some sort of intent that, I mean, it's a contract, right? I would say, I mean, if you look at the Java 8 style here, I would say, well, if this one doesn't exist, if it's empty, I wouldn't do anything. But I guess that means it's null.
Exactly.
Right? So I would not do
this is kind of a funny thing, because it's very easy to get all this logic sprinkled all over your code, which means that you have defensive coding, so you can put in some bad input data into your system, and that bad data can travel all the way through your system, and you will not notice anything. If you're lucky, you have a test that might catch this misbehavior, but probably you're not going to notice anything except some weird behavior in production. It's going to be really hard to find where along this path did the error actually occur. Because you're never going to notice. It's going to be resilient and pass through this bad data. So what you should do is like what Daniel just did here. If the data is bad, then you probably have an invariant for that, then you should just stop and handle the error, not just try to pretend that you can do, just pass it on and use defensive code constructs.
So I guess the key takeaway here is that if you have an optional as a return type of some API, you should take care of that immediately. You should do your map or else get, depends on what you do. And you should never pass your optional to other APIs or other methods.
Exactly.
Of course, your internal method, that's fine, but not the public ones.
Yes, and I'm primarily talking about public methods. Obviously, that is a part of your public API. So before you start using optional as an input argument, think carefully about if that's really what your intent is.
Right. Okay, so let's move on.
Let's move on.
We have a lot of stuff.
Okay,
Right.
so what we're doing here.
So this is another thing that's interesting when moving over from Java 6, Java 7 land to Java 8. And that comes along with stack traces. So Daniel, can you run this?
Sure. Oh,
We got a null pointer exception. And what would be the normal way to do when you see a stack trace? Well, if you're running IntelliJ, you would click that blue stuff down there, right?
Click it.
Uh-huh.
Line 36.
We all do that. And of course, the junior or the novice developer would now say, there seems to be a null pointer exception on this line. But then you need to realize in Java 8, we have introduced something called streams. And those streams have intermediate operations, and they also have terminal operations. And usually, your streams are not as, let's say, trivial as this one, where you have just, sort. You only have, flat map, filter, map, limit, skip, whatever you do. And it becomes so, advanced. And those are intermediate operations. And the fact is that those problems that we are seeing in the stack trace really happened in the intermediate ones, but the stack trace is sort of pointing at the terminal one. As a senior developer and the one that have been working a lot with Java 8, you would immediately start looking, a bit further up in the stack trace, or start looking at the intermediate operation and go like, hey, yeah, this is actually a problem in the natural order comparator. It doesn't accept null elements. So Daniel, how would you have fixed this?
Well, in this case, it seems like this is the culprit, right? So let's get rid of it. And having a stream with null values is really...
That's really bad, but yeah, let's say that was the case.
So we can just filter it out like that. That should fix it, I think.
All right, so that fixes the problem. But the key point here is that as a Java 8 developer now, you need to start, bringing in some knowledge about lazy versus eager evaluation and when it's done. That's really what you need to do when you start working with these kind of things. Okay, the next one, continue on with a little bit of streams. So here, in this piece of code, we have an imaginary service that we can use to work on items, the almighty item. And it has one method that is called items matching, and we can pass in a predicate, and then the service will return all the items that matches that predicate. So we're writing a piece of code that we want to have a specific item with an ID of something. So I create a predicate, which is basically my filter, and then I check, does the current item have the ID number 6 in this case? So I pass it in, and I know as a developer that IDs on items are unique. They're like, you can view it as a primary key, so they should be unique. So I know, well, if I get a match, I should get one item right. But I get a stream back, so what do? I can use find first or find any, because it's just going to be one, right? It's going to be one or empty. So I use find first in this case, and if present, I will do something with the item. Well, of course. I mean, you're functional now. That's what you would do.
Yeah, it's beautiful. It's one line.
Yeah.
So what is the issue here? Well, the issue is, let's say your service, it could be a third-party library, or it could be an external microservice that you call over the network. Let's say the API does not make any guarantees about this invariant that I happen to know about. It says nothing about, oh, you can filter a bunch of items, and we will always make sure that it's unique IDs, because it returns a list. It doesn't return a set, for example. That means that if we would get duplicates back from the service, using find any or find first, we would just get one of those items right. So suddenly we have a non-deterministic behavior in our code.
Come on, I don't even believe you. I mean, this code is fine.
Yeah, we'll run it.
Should I run it?
Yeah.
Okay, let's run it.
Let's run our beloved service. Okay, so it's got processed an item 6. Which has a name 6.
I'll run it again.
7. Run it again. Let's see what's happened.
Oh,
we got another one.
Oh,
it's the same ID, but a different name. So we're getting a unexpected and irrational or non-deterministic behavior. So how can we protect us from this? Well, instead of just, I'm sorry.
Sorry, I mean, isn't that supposed to be the case when I use find first?
Exactly.
I mean...
Well, you will get the first hit. but they can be multiple. So how do we protect us against it? Well, we should have let's say an invariant or a contract in our code that should check, okay, did we actually get the expected result? One way of doing that is the beautiful reduce operation in streams. So let's create, the reduce operation takes a binary operator that Daniel is coding right now. So let's create a reduce method with a binary operator that will always throw an illegal state exception. Because this method will be called if there's more than one element in the stream. Sorry, more than one item in the stream. And if it's just one item, it's not going to be called. So this should protect us against those duplicates. Let's try and run it.
So that should be good then. Let's try it.
Yes.
I guess that did it.
So now we have a contract, but we still have the function style.
And I guess you can Uncle Bob this.
Yeah.
You would do
Go Uncle Bob on it.
one item. Is that good?
Yes.
Ah, that makes it good.
So now it becomes a little bit more readable, right?
Like that.
So does it work? Let's change the ID. I happen to know that 6 has duplicates. Let's change to, I don't know, 5, for example. Yeah.
Okay.
Item 5.
5. You got
Shouldn't
5.
have duplicates, and then this method should pass, right? So now it's working. So the takeaway, I guess, is instead every time you write find first or find any, and you're doing that because you're basing it on some assumption that you have, you should think again and think, should I have a contract here? And use reduce instead.
And I think another important aspect is that you tend to do these kind of things when you start converting legacy code into new Java 8 styled one-liners. And then it's like, I know this, so this is going to happen. But then all of a sudden somebody changes what you knew, and you get that non-deterministic behavior. All right.
Okay, so let's move on.
Moving on. Underscore 8. Here we go.
Okay, more streams.
Yeah.
So in this example, we have we're dealing with a user service, and the user service can get us the currently logged in user in our application, as you can see down there on line 44. And let's say we're building some kind of, I don't know, web shop or something. So we have a list of items that the user wants to buy. So we create a stream of that list, and then for each item we can create an order. An order simply contains the item ID and the ID of the current user. And then for each order we'll just send it away to the order management system by using order service. Pretty straightforward. So let's run it. See if it works.
I'll run it again. Okay, let's see what's going on. So we sent 30 orders.
Yeah,
That's
30
good.
orders. It's worked perfectly. And after a while we decided, well, we got some issues with performance or throughput. Let's try parallel streams.
Yes, parallel streams.
That's pretty cool.
Because now we're
very
doing
easy
Java
change.
8. It's so easy to just introduce, concurrency.
Exactly.
It's a one-liner.
Everyone who's presenting Java 8 is talking about parallel stream.
I do
How
that.
beautiful it is. And of course, a disclaimer, this is an academic example. In the real world, whether or not using parallel streams would actually benefit you in terms of better performance is a totally different discussion, but we decided to try parallel streams. So let's see if that works and run it.
What? Oh,
Blew up.
you have a bug.
No current user found. Okay, so apparently I didn't get a user from the user service anymore. What should we do?
Should we jump into this and see what's going on inside under the
Yes.
hood? Okay, let's
take a
do
look
that.
at that library that we're using. Okay, we got a current user. Oh, it's a thread local variable. That's a pretty common thing to see in frameworks and libraries and so on. But that variable is bound to a specific thread, right? As soon as we go over to our parallel streams, all your operations on that stream will be executed in a different thread, one of the threads in the underlying fork join pool. And obviously, we don't have a user there.
Right. I mean, and to be honest, for us, this is so obvious now because we see, there's a thread local. Of course, you cannot use parallel streams. You cannot execute this in multiple threads. But believe it or not, when you have, those novice people, they learn about parallel streams very early on when looking at Java 8, because that's one of the cool features. So what they do is that they look at the code and they find, some data structure, stream, and blah, blah, blah. And they go like, hey, I just learned parallel streams. I'm just going to put that in there, and I made the performance go,
I can write multi-threaded code without thinking about it.
Yeah. So how do we fix this then?
Well, we can fix this particular example by changing the implicit use of a third local variable and making it, instead passing it as an explicit parameter or argument into the code. So we just, before we start the stream, excuse me, before we start the stream, Daniel just extracted the user, and then we can use that user and pass it into the stream. And now we're no longer are using something that is bound to a specific thread. So this should work, right, Daniel?
Right. Let's try it again then. See, parallel streams, explicit user, and yeah, it's 1030 words again.
And it's very easy to run into these problems, as Daniel said, because unless you actually know how your library works under the hood, then you're going to run into these types of problems. So I guess the takeaway is know your libraries, know your frameworks, and just because it's so easy to actually create a parallel stream doesn't mean that you do not have to think about multi-threaded coding and so on.
Yeah, I'm sorry, Daniel. This is the same problems we have with concurrent code. So
exactly, the same problem applies.
All right. Okay, moving on.
Yes.
So now we're entering the space of functions.
Functions and typing.
Oh, that's a cool thing.
So let's look at this. We have a beautiful method called number of free apples. And it's a function that can decide how many apples should you get after the break here. Now, it takes a user and it passes in a function that takes a user and returns an integer, and that's simply a food ratio. And then it takes that ratio and multiply it by 2. That's how many apples you should get. And as you can see, we can just grab a random user and let's run this code and see how many apples this particular user should get.
All right.
So if you're 13 or older, you will have a ratio of 2, otherwise a ratio of 1, because small kids apparently don't need to eat as many apples. So we get 2 apples right.
That's good.
Yes. So what is the issue here with number of free apples? Well, what does this method signature, does it really communicate its intent well? I would say it doesn't really. It takes a function, any function that takes a user as input and outputs an integer. Okay, we named the argument food ratio, but the signature itself doesn't really say anything. So there's really nothing preventing us from sending in a random function.
Oh, I see what you're saying. Let's see if I can
let's look at an example.
Bring that up. Here we go.
Okay, so we have another function that can calculate or return the user age. We can pass that in. It's still a function that takes a user and returns an integer. And nothing fails. No compiler error.
I mean, it looks good, doesn't it? I mean, it's a feature.
Yes, and if you're lucky, you might catch this with a test. But otherwise, you're not going to notice anything. Your IDE is not going to help you. And suddenly you will get, I guess you would get an awful lot of apples in this case.
Okay, let's run that and see.
Oh, 24 apples.
24 apples.
You can take them home.
Good deal.
And the basic problem is that we were not clear about our intent. We did not use domain-specific types, and instead we just relied on these generic types, kind of like using object as your domain object or your strings everywhere. It's the same basic problem. So if we would take this number of apples method and instead use domain-specific types, we can define our own functional interface.
Ah, interesting. Let's bring that one up.
So let's define an interface that is called food ratio strategy. It's a functional interface because it has one abstract method. You can annotate it with functional interface, and then you will get some compiler help if you start violating that contract. And suddenly, if you look at the method number of free apples, it's starting to become very clear. We do not just want a function, we want a food ratio strategy. So the subtle bug that we had in the previous example is suddenly going to be impossible to write because the compiler will refuse to compile it.
I don't know if they can see this, but it has a red line underneath.
There's a red line,
Yeah,
yes.
Okay, good.
I'm sorry for all the colorblind people, but
yeah. So, but I guess what you're saying is that this is plain old good design principles. But people tend to forget this when they have to start using this brand new tool called function.
Yes. You have this new shiny hammer. Let's go around and whack things with it.
Because function goes from one thing to the other, and that's what you focus on, and then you forget that this is actually a problem. Should we bring in another type of problem that's actually a lot more, let's say, sophisticated?
Yes, but on the same theme. Let's do that.
So the next thing is we're going to build cars. We don't know anything about cars.
And we're in Sweden, so we'll build a Volvo.
We build a Volvo, and since we're, cool, we build a Tesla as well. But we've learned about this new stuff called functions. So we figured that, this is a powerful tool. We're going to use that. And, let's just run the code once and see that it actually works. That's good. Oh, sorry, I didn't remove that error. There we go. Please do it again.
Those damn domain-specific types.
Oh, yeah. So it's green. That's good. I mean, that it works. OK. But while we were building this code, we started to realize that, wait a minute, building a Tesla and building a Volvo, that's basically the same thing. So our factories were looking really, really alike.
I know this thing called dry.
Oh, dry.
Yeah.
Don't repeat yourself?
Exactly.
OK. So we figured we would extract a generic car factory, and then we would just supply the specific behavior of an engine. See, that's the big difference between the Tesla and the Volvo, right? Anyway. So let's go into that. Let's bring in the Tesla factory. That's fine.
Okay, let's jump into that.
Okay. So here you see a typical car factory. It uses the generic car factory to create a car on line 21 there. And it passes a function to its internal engine function, or method, sorry. Okay, that's fine. And the Volvo factory, can you bring that one up? Okay, so now you see it's the same thing. It just passes a function to its own engine. But now business comes along and says, you know what? Every engine should have a generator. Okay. So Daniel, can't you just inject a generator inside of the Tesla engine?
Okay, so let's poke around a little bit. It turns out that the factory actually can create generators too.
Fantastic.
So that's pretty cool.
Let's put that in there.
Oh, and the engine wanted the generator, right?
Yeah, and that will do stuff, I guess.
Yeah. We'll take care of that later. All right, so Tesla is done.
Tesla is done. And now we push this through our pipe, and let's see what happened. Can you run the test again?
Sure. Ouch.
Stack Overflow. Isn't that a web page?
Yeah.
No. Yeah.
In this case, it's an error too.
Okay, so what happened here? We got a Stack Overflow. That usually means, infinite recursion or an infinite loop somehow. But you just invoked the generator method. I don't get it. Can you jump into the generic factory?
Generic factory.
So we see here on, there we go. On line 30, we see that that's the create car method. And that took that function to that internal engine method inside of the, let's say, specific factory. And it applied itself on top of that, and it creates that generic car. But inside of that internal engine method now, we're invoking generator method. And that turns out that it also had a dependency to the engine somehow, actually the horsepower. So that was a rookie mistake, I guess, inside of that class. But neither your IDE or the compiler actually saw that this is creating an infinite loop now. And this is really because we have injected behavior through the function API. But there's another thing that's really wrong. What about encapsulation?
Kind of breaks that, right?
Yeah. I mean, when you do classic OO style in Java 6, 7, or whatever you use, you're really careful about this. You say this, this method is private, this one is protected, this class is package local, and so on. And you spend a lot of time. But all suddenly, you have functions, and this can go across modules. There's like no access modifier. You're saying, hey, here's a function to my internal thing. Please invoke it whenever you want. I have no control. And then you get all this crazy stuff. So you need to be really, really careful when you do these kind of things with functions. Although functions are great, but you need to make sure that you use them correctly.
So let's move on. So what's happening here?
So now we're going into the space or realm of lambdas. This is what we like. This is what we feel like, yeah, I'm going over to Java 8, I can do lambdas. And the first thing that comes in mind that you need to know about is, of course, how things get evaluated. So can you just run that? OK. So what just happened? I seem to invoke this isEven method inside of that filter operation down there. And it's done even though I'm not really using the end result. And as it turns out, Java is a language that's using applicative order. And that means that this statement is going to get executed whenever applied, as soon as it appears, not when it's needed. In another language called Haskell, you actually have normal order. And how funny doesn't that sound? Normal, because we're all used to applicative. That's really what we're used to. But in normal order language, you actually have the notion of, I'm not going to evaluate it until it's actually used. So Daniel, how would you simulate normal ordering now when you have the option here in Java 8?
Jared, I can fake it. I can make the abnormal ordering a normal ordering. No, it's become too philosophical. But I can use the good old supplier, I guess.
Yes, the supplier. We like that one. It's kind. He just gives.
There.
So by a tiny little trick, Daniel placed that piece of code that we didn't really use inside of a lambda. And we know that lambdas have the ability to execute at a later stage, or being lazy. So let's run this again.
Did it work? It did.
It did. Fantastic. Okay, what if you would replace hello now? Can you like really fetch that data still, or is it
if
gone?
I want to use, invoke the supplier.
Okay, so let's go that again.
I suppose it should be evaluated again. Right.
Okay, so we got the same thing. So you might ask, like, yeah, this example is really easy. I mean, why are you even showing this? Well, as it turns out, this is a very neat tool that everyone should master when transforming legacy code to new style Java 8 code. Because it could be the fact that, I'm changing this part here, and I have a dependency to this legacy thing, and now I can decide I only use that inside of this little branch here. And I can put that in a supplier and actually use it. And I don't need to pre-calculate it because I've refactored this other part here. And people tend to forget about this. Okay? There we go. So now we're really warmed up. Now we're moving in to some advanced Lambda stuff. Most developers tend not to understand the difference between something called stateless and stateful lambdas, or non-capturing versus capturing lambdas. And if you look at this piece of code, it turns out that this code is actually using a capturing lambda. And Daniel, can you please show how?
How can you tell? I mean, the syntax, there's only one way to write a lambda, right?
Right. How would we know?
Is this a difference? No.
You can't type it, though. You can't
No,
say, I want
okay.
to make it stateless.
Then I guess we need to go down to the basement, right?
Right. We need to go deep, deep down.
We need to start checking out some bytecode. Finally. So let's compile this class, see what happens. Compile it, and then we, I guess, decompile it.
And you're all familiar with the Java P command, right? I mean, you all inspect Java bytecode every day.
That's what we do for
Right,
breakfast.
good, good. Yeah,
Okay,
that's
so
what you
here it
do.
is.
Fantastic. Hope you can see this. Yes, great. So, I mean, this is there's a lot of arguments that you can pass into the Java P tool, but this one actually gave us a fairly good description of what we have in there.
So I guess here we can see that we're invoking something by invoking dynamic. And we're actually invoking this
That's
lambda.
our lambda. And that lambda is placed inside of an instance method. And every time your lambdas are placed inside of an instance method, that means they are capturing, or they have a dependency to the lexical scope, this. In order to execute that lambda, we need to reference this. Okay, so let's go back to the code. If you would actually say this dot pattern, I think that would be even more explicit. So now everyone sees, like, yeah, I actually have a dependency to this here.
So you're saying there's a difference there in how the bytecode will turn out?
Yeah.
Okay.
Oh no, that is exactly what you did before. But we want to make this stateless. And now you might say, okay, so why? It turns out that if you want to unleash the full power of lambdas, you should make your lambdas stateless. They're significantly faster. Brian Getz talks about this in several talks, and he has all the numbers. So in case you run into him, please ask him how fast they are. How would you make this one a stateless?
So I guess what you're saying, if we try to avoid accessing the instance variable,
Yes, that's
then
that's the key here.
So I guess one way to do it would be like this. Let's turn this back to
Oh,
something.
sweet. Would that be it? Because, I mean, a very important aspect here is that the method all matching elements has a dependency to this. But the lambda, arrow E contains pattern, doesn't. So compile this and let's see what's going on.
Okay. So can you walk the talk? That's the question.
Walk the talk. There we go. So now you see.
Oh, look at that.
It's static. And under the hood, it actually means that the machine can actually use the same lambda object over and over again. It's a singleton, and it can actually inline this. When it was stateful, you have to create a new object every time. And well, to be honest, in the worst case, the performance that you get is of inner classes. So it's not terrible. But it's not as good as this one. I mean, this is way faster.
Okay, but seriously, Daniel, this is starting to look a bit ugly.
But that looks
Like
kind
all
of
these,
ugly.
Local variables, right? I don't like
Yeah.
that. See if we can do something different.
Okay.
I know this trick.
Is it called Uncle Bobbing it?
Yeah.
Yeah, let's Uncle Bob it.
So now it actually got more readable too, I guess. There you go.
Yeah, let's just expand that one. Yeah, there we go.
There you can read it. Okay, so I extracted the lambda to a method, an instance method, right?
And that
So
method...
This should be the same thing, right? We're no longer using an instance variable within the lambda.
Right.
It's up here.
And you can remove that this dot thing too. That sort of is annoying.
Yes.
There we go. So now you just made everything more clear and explicit. But can I trust you? Let's compile that and look at it again. I mean, this looks kind of magic. It looks like, wow, that should have been the first thing you did. Yes, you're right.
Oh, yes. It's still static. And there's our matches method.
Ah, fantastic. We're using that to invoke our lambda that is static, and therefore we got all that performance that we wanted.
That's pretty cool. So just by writing readable code, you will actually get more performant code.
Yeah,
It's pretty sweet.
that's sweet.
So
But
you don't have to think about bytecode. That's good. I don't like to think about bytecode when I'm programming.
But another thing, though, is that you will say, oh, well, this example was so easy. Well, as it turns out, when you're refactoring your legacy code, once again, you're starting off with one method, and that method has dependencies to fields, internal methods, and so on inside of your class. That's when you need to know this. You can say, hey, I'm doing this, I know what I'm doing. We do have a capturing lambda right now. You put that as a to-do, refactored all those other things, or whatever you want. Or you start refactoring that entire thing and make it as beautiful as you want. Or you can do these kind of tricks as well. So it's really handy. All right. Oh, 9:40. I think we have a time for another example, don't we?
Okay, let's take a
bring
short
one more in.
I guess this.
Yeah. The thing was that when we set up this presentation, we have so many examples. We figured, oh, let's pick 10. That's a good number. And we said, well, we can also bring in these ones in case we have time.
Okay, so let's talk about streams, right? Go back to streams. So what's happening here? Let's run this. See what happens, right? Okay, we have a list of integers, 1 to 5, create a stream of it, and then we print all the elements within the stream. 1, 2, 3, 4, 5. Perfect. So let's play around with this piece of code. Let's add something to the list.
Should we add something?
Yeah, add something to the list after we created the first stream.
Okay, yeah, okay, that's good. Like this, like add 42, favorite number.
Yes,
yeah.
that's a good number.
Uh-huh.
And now let's create a new stream of this modified list.
A new stream?
Yes.
Okay.
I don't know.
So stream 2. Is that good?
Okay, and let's print that one.
Oh, you want to print it?
Yes.
Okay.
Let's see what's.
So stream 2.
Okay, so the question is, what are we going to get printed here?
I mean, isn't
Any
it
ideas?
obvious?
What do you think?
We will get 1, 2, 3, 4, 5, 42. No, sorry, stream 1 would be 1, 2, 3, 4, 5. Stream 2, 1, 2, 3, 4, 5, 42.
Okay, kind of makes sense. Let's try it. Run it.
Okay.
See what happens.
What?
Ah, look, they're the same. Now, why is that? Well, the reason for this is because streams, the way we're using it right now, they are late binding. Which means that you're not going to bind to the source for the stream until you're actually using it, I guess, when you invoke the terminal operation.
How would you know that?
Well, you could know it by attending this talk, and you could know it by reading the Java doc, because if you dig down and look at this Java doc, I hope you can read it, yes, you can read it, start talking about a splitterator, and you got to override this if it's not immutable, concurrent, and late binding. There's some information there. So let's jump over to splitterator, and there's a bunch of text. Scroll down, and we can see there's some implementation specification. Okay, so it says the default implementation creates a late binding splitterator. Okay, so there's the answer for why it behaves like this. And if we jump into the actual method stream and see what that does, well, it just goes off and creates a splitterator, the default splitterator. So since it's late binding, it means that, as we just saw, you can modify this mutable list that we have, and both streams are going to see it.
Interesting. But I guess this wasn't the really intent. But now when I know that splitterators are late binding, I need to actually create a new array, can type list like this, right? Isn't that what I need to do?
Okay, so now you're creating a copy. That's true. So you're not modifying the same list anymore. Or you could use an immutable collection. Then
that's right.
You have no option but creating a copy. That's good. That's a solution. But that's actually very good to know, if you didn't already know it, that streams are late binding, because you can run into problems if you write code that are similar like this.
So I guess the key takeaway here is that, well, this one is obvious because you see it all. But if you have methods that passes streams to other objects, you need to make sure what you're doing. And of course, you need to pass on a very specific stream. It needs to be bind to a certain, let's say, snapshot in time. Because otherwise things get modified and you're not sure what's going to happen in your code. Okay. All right.
So
9:45. I think we have 5 more minutes for Q&A.
Yes. I don't think we have time for more examples. Let's do some Q&A.
I think we need a mic or... There it is. You're under a spot now, so yeah.
I just want to ask if you could force an early binding of that stream.
Yes, if you would, I guess if you would have provide your own implementation of a split iterator, I mean that could, I mean you can do whatever you want, I guess. So, or do you have any other ideas?
Not from the sleeve,
No.
on the spot, no. Anyone else?
So how many of you are actually not doing Java 8 now?
On a daily basis, like
On a daily
in
basis,
your
of
work.
course. Okay.
How many
Good.
of you have a plan for transitioning to Java 8? Or know at least some point in the future? Okay, interesting. And how many are already using Java 8?
Wow.
Wow, it's a good adoption.
I hope everyone found something inside in this talk that they, yeah, I need to bring that back to my project, or when I do this, I will keep that in mind. So thank you so much.
Thank you.